Good afternoon, everyone. I'm Nambi Seshadri, for those of you who don't know who I am, a professor of practice here at ECE department here. It's a pleasure to, so this is a graduate seminar course as well as open to the larger community at large, having to do with a whole bunch of interesting problems, challenges industry faces in all aspects of broadband communications, networking, and storage. So over the course of this entire quarter, I think we have nine talks. One got over last week, and it's a whole bunch of assorted topics ranging from physical layer issues, which we will get into in the next several weeks, and topics such as what Dr. Sherman Chen will talk about today, having to do with video transport and IP networks and the challenges thereof. We will have talks on storage, and we have someone from Western Digital to come and talk about that, as well as look, we're dealing in a world where we know about we want to know where everything is precisely and where everyone is precisely. At least some of us wants to know, and we will have someone from Google to talk about location and Android. So it's a whole bunch of very, very interesting talks from the industry, and I hope many of you, especially the students, can take advantage of these folks coming, and more important, they have generously given us the time to actually stay back after 6 o'clock, after the talk, probably spend half an hour to 45 minutes. So make use of that time to actually interact with them and ask whatever you want. Can I get a job in your company? What would it take to, what fields are interesting to work on, to other topics which hopefully are relevant to your career. And you will see most of them are not one-dimensional. They have gone through, like Sherman Chen here would have gone through pretty much the whole evolution of the industry. So most of them are extremely senior speakers. So Sherman, for example, has been there, has seen the world of digital TV from day one, so from the trenches. So he has seen the first MPEG to HDTV terrestrial broadcasting systems and develop chips for that, but subsequently through the whole broadband transport of video and generally broadband technologies across the whole space. So he's currently, Sherman has so really urged the students and to take full advantage of that, and bring along your friends, so you really can see where the world of communications and networking and so on are really moving along, and you would have the chance to interact with the speakers. So briefly talking about Sherman actually is Vice President of Engineering at BROADCOM Corporation. He and I worked for nearly 15 plus years together. He was my peer. While I was focused on mobile and wireless, Sherman was focused on the wired portion of broadband business. So you're essentially dealing with every single form of broadband technology, and in particular cable modems, DSL, passive optical networks, and then the associated video and audio transport over that. So he has driven a whole generation of, and it's probably amongst the most mature and successful businesses of BROADCOM, probably number one in every one of those spaces. And he leads a very, very, probably one of the most experienced technology teams that you can find in the broadband space anywhere in the world. So he has a PhD from USC, and I have urged him to spend a little bit of time talking about generally the state of the industry and so on, but the talk is a fairly technical talk on a mathematical theory of compressed video buffering, traffic regulation for end-to-end video network and quality of service, and all this is, it's truly a remarkable piece of engineering to put all these things together, and Sherman will cover most of it. Welcome, Sherman.
Thank you, Nabi, for the introduction. So it's very hard to put a topic together to talk to students, right? So because you have to see how does it link to the industry, right? Practice. They are quite different, frankly. So what I will do is that I'll straight go into the topic. So we'll be a little bit mathematics. So I know some people may not like it, but it's needed, easy to understand, as simple as possible, right? So the topic actually slightly changed the title, try to fit in better for the content, but it's still same material, okay? So today's talk really about the digital video transmission, right? Especially in compressed domain, and about the data buffer and timing. So we always talk about digital video, and actually underline how to transmit it, right? Is more important. Actually, I mentioned to Nambi in the field, right? People talk about video compression, all those algorithms. Actually, in the field, right? When you deploy the product, 90+% of issues related to transmission, not actually in the video compression standard, and you don't make mistakes there in general. So, all right, let's just start with the talk very quickly around so what is the digital video? Let's start from the very basic stuff, right? Video sequence, actually, everybody understands. It's a bunch of pictures, and you have a resolution, right? And for Ultra HD, you have a larger resolution, HD is smaller, and the SD even smaller, right? Each pixel, you have bit per pixel, right? Basic 8 bits or 10 bits or 12 bits. You have those. And you have color space, you have 3 components, could be RGB, and YCBCR, right? The bottom example was a very commonly used YCBCR, 420, right? For most of compressed content in that format. Then you have frame rate. Basically, it's a fixed frame rate, has a fixed duration between frames, okay? And because it's characteristic, you can see for each frame, you have fixed number of bits, okay? That's the case. If I put this one into a transmission without any compression, what it will look like, okay? For the transmission, you have a bunch of pictures. As I mentioned, you have fixed frame rate and fixed resolution, and then sent to a transmitter through channel, then arrive receiver, okay? Because we're doing transmission, there's a timing involved, right? We have to define time. Let's define 2 simple time. Let's say we define T sub TS sub super I is a transmission start time of I's picture, a specific picture. And similar, and we define the presentation start time of I's picture, right? Is T sub PS super I, okay? Since they are fixed frame rate, then in both sides, where you will see delta T sub TS super I and delta T sub PS super I were equal to frame duration T, right? Very easy. I try to go slow and beginning and getting faster, okay? And so that's basically what required. If you transmit this thing through a lossless channel, right, that's what required. You have to duplicate exactly in the other side, all right? So the next thing happens is that, okay, when I do the transmission, this uncompressed video, you have delay. Actually, you will have delay between T sub TS I, super I, and T sub PS, right? Basically, this tool has a delay. Assume you have N frame delay, NT, basically, okay? Without loss generality, very easy to understand, right? But because this will map to compressed domain is more complicated, okay? Then what will happen is that since you're doing transmission, next thing you will need to look at it really is the rate, okay? You have a few rate involved here. You have the transmitter input rate, the R sub T, okay? Then you have another rate, R sub C, which is input of the receiver rate, and also you have R sub R, which is the output of the receiver rate, okay? Then for this rate, let's look at the rate equation, okay? First, for R sub T, you have this equation here, okay? Basically, what happens there is that if you integrate from the transmission time of I's picture to the presentation time of I's picture, what you will get is that you have an N picture, right? In here, I spell out which N picture actually you're integrating, okay? It's from Pi plus 1 all the way to Pi plus N picture, because NT is N frame in between, right? And the other side, look the receiver side, is now I mean this side. If I integrate for the same time interval, what do you will get? You also will get N pictures, but it's different N picture. Basically counting backward, right? If from I minus N minus 1 all the way up to P sub I, okay? But since each frame are fixed size, okay, you end up they're the same, okay? On the line they're different. And also you can see you have the fixed frame rate, okay? You have a total bit per frame multiplied by frame rate, you got your bit per second, right? Remember, this is not an assumption, it's a fact, okay? Otherwise, you're not doing lossless transmission, all right? So All right, so, but a little bit caveat in here. So I have this delay. What this delay really will do for me? Okay, you could have a channel which is have a delay and jitter, right? Delay for sure, and jitter possible, right? So basic assumption will be the T sub PS super I minus T sub TS super I has to be larger than this delay and jitter, okay? In order to make the lossless transmission, that's basic condition, easy to understand, all right? Now we have to look here, how about the rate in between? That's more interesting. Actually, it's the main topic for today. Actually, it's a challenging thing for the compression and the video transmission. That's the rate in between, right? So let's look the application, okay? For many video application, every picture in the video sequence must be delivered, right, in a specific time, right? You have to have the decoding time, and by that time you have to decode, right? And then make sure the picture is there. All right, so to do that, we have to examine the actual receiver. Look at the receiver in here. Now you have the rate coming in here in this R sub C rate, right? And also, let's assume each buffer has size of the one picture, okay? Because it's synchronized, right? One after another, one is in, and the other already been presented, right? So that's basically the assumption in here. If I look at the receiver, the buffer, now this buffer is this one, right? What can I observe? This is really in plain English. If I look at the presentation time, okay, all the bits from I's picture are in the receiver buffer. I's picture goes into this buffer because in my presentation time, it better be there. Otherwise, I cannot present, right? And also, all the bits from the picture before I's picture has been received and presented, already pushed out. Okay, there's no more bits in that in there. So you can represent by this inequality. All right. Very similarly, for other side, right? For this time, there's no bits from the next picture, I plus one picture, being received in the receiver buffer. Okay. If it being received, remember my buffer size only have one picture. If one bit show up in here as a presentation time, what happened? Because it's FIFO. Other side, one bit for this I's picture will be pushed out. Okay, basically you overflow the buffer. These two conditions basically saying that this is ensure the buffer neither underflow nor overflow. Okay, but by the way, you put this together, you got equality, right? This is very simple for this video. All right, simple, easy to understand for the uncompressed video. Then it will map to, then it will be easier next one. So let's look at the parameter set. Okay, we talk about the compression. We got to talk about a non-compression video, right? We talk about the resolution, bit per pixel, and color space, right? Then we have buffer. Then you have the delay, right? Those are the key parameters to drive this type of model to happen, right? Those are the minimum parameter you have to deal with in the video transmission. Okay, that's a set of model. In here, obviously, I mapped to the details. In this model, simple, uncompressed video, what it look like, all right? Now going to actually application, okay? So from analog TV to digital TV, from standard definition the digital TV to high definition to 3D TV to Ultra HD TV, as you can see, resolution change from 480i, 480p, then to 1080i or 1080p, right, in HD space, and then to 4K, okay? You can see, bit rate getting higher, and size getting bigger and bigger. Basically, you require higher quality and high bit rate, right? However, if you want to transmit original video, right, for the high quality application, it requires a lot of bits. And also, you want to store those video, that's tremendous, right? You don't have so much of a storage space. What do you need? You need compression, right? But unfortunately, if you're just doing lossless compression, it doesn't fit because lossless compression will link on the actual content. You cannot control the bits, okay? Because content dependent. So you really need in here really is high quality lossless video compression. All right. Okay, talk about compression, everybody know, immediately think about it. Lossless compression is linked to the rate distortion, right? Everybody probably in here learned about information theory. And as you can see, actually, rate distortion theory really is a theoretical discipline treat the data compression, right, from viewpoint of information theory, right? Basically in there, actually key point really is that for known source statistic property, this is the key. You better know those statistic property, right? then the rate distortion function will give you, will basically obtain, this is the lower bound, right, without assuming any specific coding method. Okay, that's in theory. But you can look at the right-hand side by this equation, right? Basically, the minimize this differential entropy, right, from the source and reconstruct the video, and under constraint of given distortion, right? So this basically RD represent minimum achievable rate for at the distortion D, okay? And in here, usually you can see that people draw those type of curve all the time, right? The distortion function really is a monotonic decreased function, right? And what I want to point out in here, this is crucial from industry point of view, only certain region of those really meaningful, right? First of all, you have to have a bound. This D really is the distortion, maximum distortion allowed, which means that beyond that, there's no commercial value, okay? So I mentioned to a couple of professors early that for the compression, this is very important because we do see many academic work try to push to here. Okay, basically, I create an algorithm. I can do 500 to 1 compression. I'll give you an example like Fractal 25 years ago, and also some wavelet-based compression. I can do 500 to 1 compression on an image, right? And compare with JPEG compressed image, I can say, hey, look, that one is quite a bit better than the JPEG, which is true, by the way. But if you want to sell it, nobody will buy it because both like a garbage, right? So basically, that doesn't help. If you really want to do that, you know, that's will become your hobby. It really doesn't help. However, for given distortion, how about I can have this target given distortion, which is sellable content. I can reduce bit rate by half or something, right? That would be really valuable. But that is extremely hard to do. Okay, that's the tough part. So I want to mention here, I will go back to this later. So in practice, right, I will say in general, it's really hard to compute RD in real world video. Okay, basically here's the research problem actually we can extend. I mean, today you have all kinds of tools, right? Not like 20 or 30 years ago, and tools are very limited, right? Today you have machine learning, all those really fancy tools, right? You can extend the model to maybe a Markov, embedded Markov, and also could be a Gaussian mixture model, right? Basically used in machine learning, and twice facilitate to see how to generate a good statistical model for the video source. Is there this type of thing exists, right? So it's a good thing to look at it. And the other,
Sherman,
yep.
Question.
Go ahead.
So for today, you obviously in your implementations you need to know some kind of rate distortion function that you're using because
that's coming next.
That's coming next.
Yes.
Okay.
Okay. All right. In the practice, actually, we're not dealing with this type of rate distortion. By the way, I want to say a story. This is being found by the Academic Society 20 years ago. Actually, Toby Berger wrote a paper 20 years ago, talk about this at one of the celebration event for Shannon theory 50 years, right? He wrote a paper called Lossy Video Coding in the attribute information theory transaction, right? What he wrote, actually, I put on my notes in here, but he wrote is that, okay, rate distortion theory is elegant, but however, the impact of rate distortion theory on practice of lossy source coding or compression was very slight. And then he went further, right? Even dig out why. So basically what they said is that, the part of the reason is for this elegant theory not influencing the practice of data compression can be traced to the observation that the practitioner of information theory and the designer of the data compression system form a mutually exclusive set, which means there are two groups of people talking about different things, pretty much. So sadly, that's true. So let's look at practice, what do we deal with? In practice, you never can say, hey, I don't have to make an assumption of a specific video coding method. You do, you have to create one, right? So what happens is that actually rate is really a function of the resolution, bit per pixel, color space, frame rate, and coding method, and the distortion. Not just R and D, R and many others. Okay, that's the thing. I will come back to actually how to link to the rate distortion theory. That's a good research problem. So now we talk about the coding method. Actually, coding method is commonly called the video codec. Okay, that's the word being manufactured by the standard people. So here is basically a timeline of some key video codec. Okay, And some major one, like MPEG-2, AVC H.264, and HEVC H.265, probably you are very familiar with what it is. And then some minor one, right? Through this thing actually spanned more than 30 years, right? There are dozens of video codec being generated, okay? The minor one including the video phone related, right? H.261 and 3, and also MPEG-1, MPEG-4, and also a bunch of others, right? There's still other I didn't list here. China has AVS and VP9, VP7 is from Google, and also Real Network has Real Video, and those are the key codec, actually. The lately, also another one show up just this year, right? There's a new one called Align from the Align for Open Media, right? Generated this is called AV1 codec. So that's the latest one. So since we talk about video codec, let's look a few major ones, which is really meaningful, right? So here it shows 3 generations of the key video compression standard, right? Actually, MPEG-2, H.262 really enabled the standard definition video compression and also DVD, right? H.264 AVC, right, really support HDTV, Blu-ray, and video streaming, right? The latest H.265 MPEG HEVC applied to Ultra HD, right? So this is actually developed 10 years apart, okay? Every 10 years come out of a major standard, right? And each codec generation, right, is doubling the coding efficiency, okay? What it means is that if you see for content, MPEG-2 can compress 100 to 1, you will expect AVC can do 200 to 1, or HEVC can do 400 to 1, roughly, okay? So the question really is that this is a lot. You are doing a lot of compression. Why you still need it? It seems like until industry or academic go nuts, right? Why you need more, right? So, but the reality is not as simple. Look at the content source, right? From SDTV to HDTV, then to Ultra HDTV, each generation of video service more than quadruple the data picture rate, okay? Using compression, it barely makes the bandwidth storage requirement in check, okay? The compression rate increases much slower than the actually pixel rate, okay? That's why you actually need it. Then the question is that I already achieved 400 to 1, still have room or not, right? That's the key question. So it turns out we still have room. So here's one example on a test sequence called Kinomo, right? Which is HD movie content, right? You can see here's the compression from HEVC, right? This axis really is the quantization level, right? Quantization level basically measures the distortion, right? You higher quantization level, you have high distortion, and here's this side is bitrate, right? And also we put estimated rate distortion bound. That's basically within this framework of HEVC, AVC, those type of framework, right? You can create a bound using a KL expansion and transform, right? In the transform domain, you measure that. So you can create those bounds. You can see quite a bit of room still there, especially, as I mentioned, for the meaningful range of the quantization, which is this green bar and below that, right? You can see pretty large gap, okay? It's quite interesting if you look at the behavior of this, right? So one thing that's quite interesting really is that, seems standard doing pretty good job in this range, okay? But they did a poor job, absolutely poor job in this side, okay? So this really is a problem. Actually, if academic can help, that would be great. Basically, that how we are improving this side. Okay, it has a true usage, right? Why? Because today most of the content is in HD. The next phase will be 4K, 8K, right? When you have a higher resolution, guess what? The quality requirement will be higher. You don't want to buy a 4K quality. You want to get 4K quality. You look like HD, right? You don't want that. So, what that means? It means the quality will shift to the left, right? The requirement. So, all right. So that's one of the things actually quite interesting. Okay, down the road, right? Moving forward, you will expect the video compression standard continue at once, right? For example, new compression standard, I already mentioned AV1 from the Open Media Alliance, and also MPEG actually in this minutes, right? They have a meeting in Asia, actually in Macau, right? The standard body is doing the MPEG, they call VVC, versatile video coding. Also, eventual name will be in ITU side will be H.266. The target application will be 8K 360 video, AR video, VR related video content. Okay, that will be something to watch. Maybe eventually we'll achieve 800 to 1, probably the target they will try to do. And I don't know if they can achieve that or not, but that's the goal. All right, let's look a little bit about video compression. So itself, okay, now we said we'll tie down video coding method. So basically you can see you have video sequence coming to a compressor, video compression engine, then come out of bits, right? Each bits have reduced, each picture has a reduced number of bits, and usually the size are different, right? That's we all know. But look at this video compression algorithm. I'm using H265, the latest HEVC, right? Standard. You can see it's a pretty complicated system, right? This is a typical hybrid motion compensation transform coding, right? I believe people here already learned the compression. I don't need to say too much about it. But I just want to say that really this is a complicated one, right? Pretty much you can play all the tricks from coding unit coming in to do transform quantization. Then you have an inter prediction, right? Loop filter, right? Doing all those tricks with a very fancy arithmetic coding, right? And all in place. And you try to address that. And also, I know some professor in here work on the mode decision, right? The mode in here is super complicated, many modes. Probably today, if you really want to do a full search, right, to test those modes, they become not viable in real-time implementation. Right? You probably can apply some of the machine learning, those type of trick, and to do that, right? And that's HEVC. Actually, AV1 even worse. You are bet on the next generation encoder, whatever they call MPEG VVC, will be maybe a couple times worse, if not 10 times worse, right? So, yeah, that's basically is for the transmission. For the decoding side, it's much simpler. You can see the diagram is much simpler from entropy coding to the inverse transform, inverse quantization, to the intra prediction and also compensation. Then you through the loop filter and you reconstruct picture. Pretty simple, right? But on the line for the application, it also varies. So it's very different in this regard. So because application, you will expect, look at those parameters I said in the first page about resolution, bit per pixel, color space, and the frame rate, right? You can see some of the parameters will change. For example, in the compressed domain, now your resolution may be reduced because the bandwidth doesn't fit in the situation, right? And also your frame rate may be reduced. Right? You could skip certain frame if it doesn't fit the transmission. And in general, for the video coding, bit per pixel and color space will not change in the video coding. Today it's never changed. However, with the latest application, if you count on the post-processing, this one I still have a post-filtering, right? If you count on those, in the new application domain, it does change. Especially for the latest one, people probably heard about high dynamic video, right? HDR, high dynamic range video, HDR. For those video, because your color space change, then the bit per pixel change. It's not 8 bits, it could be 10 bits, right? Even higher, depending on the domain. So that's a lot of a changing parameter in that sense. So overall, right, what is the real objective for video compression algorithm? So you have to understand what actually is useful. I'm list the 2 typical applications here. One application is the top one in here. Basically, it's really say high quality video application, right? When we say high quality video application, which means that Ultra HD content being put into Blu-ray, put on this Blu-ray, right? And also transmit through the broadcast channel, just like you watch cable video, right? Usually, those require very high quality. You don't reduce resolution, and bit per pixel and the frame rate. You don't change any of those, right? You do compression, you don't change that. In there, the objective of the algorithm really try to make sure your rate fit in distortion target because you don't change the resolution and the other factor, right? However, in the other application, like the OTT video streaming, which is used in your YouTube, Netflix, and those applications, right, which require bit rate to adapt the channel rate, okay, then the situation changes. You can see your compression objective really will have this rate, right, related to the resolution and frame rate, and also distortion, but it has to fit in the channel, okay? And also now the distortion has to be smaller than some distortion target for given resolution. Okay, that really changes. It's a typical ABR we'll mention later, right, as an application. Okay, actually, the world has changed. So when we move from analog TV to digital TV to HDT to Ultra HD, if we follow top part, your quality will getting better and better. But unfortunately, now we also go through different route because now IP video show up. I really want to use this on IP. Then your performance actually going backward. Your new IP video quality is worse than before, actually. But we'll just go this way, right? Once you pass this stage, when you have sufficient bandwidth, you will demand top. The user will demand top, trust me. So that's happened before, all right? So the key parameter, I put listed here again, actually, we already talked about it before, is resolution, bit per pixel, color space, and bit rate, and the frame rate, and distortion is a key factor for video transmission from the encoder compressor to the decoder in the receiver side, right? That's basically a key parameter in that sense. So now let's look into transmission. So transmission side is more interesting. Really want to see what is the encoding, decoding timing, right, for those compressed picture, right? Now you want to transmit, it has to have the right timing, right? And it's relevant to your compression, also more relevant to your transmission, right? And before we do that, let's look at the coding structure. I want to say a few words that probably everybody understand already. The compression basically you have different type of picture, right? How you have independent coded picture, you have one direction predicted picture, you have two direction predicted picture, right? That's basically what it is. For presentation in the receiver side, you follow the same order as your input. Very easy to understand. However, decoding, they're different, okay? Because I have a bi-direction prediction in order to get B2, for example, right? I have to make sure I already get P4 decoded. Otherwise, I don't have reference, right? That's very easy to understand. So you will have the so-called decoding or transmission order. Actually, picture in transmit in this order, okay? Okay, if you put the picture into the system, now you have this video coming into the compression, then go into encoder buffer, then to the decoder buffer to decompression, then you reorder because you have this order problem, right? Reorder picture, pump out, reconstruct picture. All right, so few timing information we have to define. The first one really is called, now it's compressed, right? Compression you call encoding. And decoding means decompression in here, okay? This is a common word. If you go to industry interview, you would say, what is the encoder means compression, okay? That's for this domain, actually. So T sub EJ is defined as the encoding complete time of a J's picture, okay? T sub DJ represent decoding start time of J's picture. One is the encoder buffer side, one is the decoder buffer side. Okay. Then you have presentation start time of J's picture. Okay, define. All right. So as we said before, uncompressed data also has a fixed frame duration, right? Which means the two encoding time in the adjacent frame and two decoding time adjacent frame, they are subjected to equal to the frame duration, right? That's easy to understand. Okay. So now I got those timing. So in many cases, those time notion, right, whatever you labeled, can be carried using timestamp through the string, put into the string, carry it to the other side, right, in order to synchronize. Okay, that's basically one thing. Let's carefully examine actually the video buffer. We talk about the previous page, we talk about here the buffer. Now let's zoom in on the buffer. Okay, what buffer really look like, how to associate with the timing notion, right? So first thing we notice that, okay, for this buffer, you have an input and output, right? You have a bunch of rate. The first rate really is the encode buffer input rate, and also other side really is the input buffer output rate, and also the input rate of the decoder buffer, right? And other side it really is the decoder buffer output rate, all right? So, and we define few things in order to fit in all the timing notions. First of all, for J's picture, that moment, right? We need two notions. One is that the size of J's compressed picture. Assume here's the size, P sub E, J, okay? And also, by that moment, right, the video buffer has a buffer fullness. It's a previous picture and some of the bits still in the buffer, right? So basically, we call the video buffer level right before J's compressed picture completely input into the video buffer. These two basically count for encoder buffer fullness, okay? And the decoder side, we also specify, hey, you got to have a size, right? Specified size, otherwise you cannot make the design, right? So that's the buffer size. So, and also, we already talked about the encoder time and decoding time, right? Assume those has a fixed delay for every single picture, okay? The delay is a constant multiplied by t, Okay, so constant, assume the constant is integer. It doesn't lose generality. Actually, which is basically you have a C frame buffered in those buffer. Okay? Then you will see, you can imagine, right? Buffer will spin because it's compressed. Now the thing will spin from left to right. This side go low, other side go high, right? The type of spin. All right. So with that, you can see in the, actually, there's a model, interesting enough, right? With a few notions, this is as far as I will go for mathematics, very simple actually. You can see, you want to make sure if I examine my decoder, right? I want to ensure my decoder buffer never underflow, right? Also never overflow. Guess what? That will guarantee your timing, okay? How does it associate with timing? That's exactly the relation. When you have the buffer fullness, we defined in previous page, and also the as picture, if this one less than this integration from encoding time to decoding time for the rate you input, right? If this one's condition guaranteed, your buffer will not underflow. Okay, and similar thing is true. If integration from a J's picture encoding time to J plus 1's picture decoding time satisfy this relation, which means buffer fullness picture plus the maximum buffer size. If this is satisfied, you will not overflow. Okay, all right. Remember, this is the shifting kind of equation. I apply to every single picture. Okay, hold for odd picture. Really, to show the constraints of the size of the encoded picture, channel transmission rate, encoder-decoder buffer. Okay, by the way, magical enough, this one didn't put in constraint on this encoder buffer input rate and the decoder buffer output rate. There's no constraint on that. Quite interesting. You can think about it. Why is that? Quite interesting. A bit deeper, but I will not discuss in here. It's a challenge to understand. Okay, we got this basic relation about buffer. The next thing we will do, we really see, hey, what's the key parameter? Here's the parameter. For a system fitting this model, what the key parameter to drive that? Really is a unit bit rate, buffer, delay, frame rate, encoding time, decoding time. Remember, resolution, bit per pixel, all those disappeared. Which means, magically enough, your compression can be can be separated with the transmission. Actually, in this case, what it says. So, okay. And I have a specific in here. I don't need to go into detail. Basically, that's how the minimal set of parameter will fit. Basically, you're fitting around those relationships, right, on those parameters. Okay. Now go a little bit deeper. Okay, I got this video buffer. So what buffer, behavior look like, right? You can see I have the input rate and output rate, and then output rate will equal to the channel rate equal to the input rate of the decoder buffer, decoder buffer output rate, right? If you measure any moment, you can see this equation hold. That's easy, right? So for the t plus tau moment, the buffer fullness equal to the buffer fullness at the t time plus the integration of the input rate minus output rate, right? That's straightforward, easy to understand. Same thing true for the decoding side. You will see this type of pattern if you measure it roughly. You have the picture each time begin to pull out, and once picture being put in, right? And the decoding time begin to pull out. Right? That's basically what it looks like. And end-to-end delay from encoding to decoding time is CT, right? And C picture within that. So, all right. Now, there's the problem. This doesn't still tell the whole story. What we really need is that, okay, for real-time application, we need a buffer model to verify I code a video string. How can I know it's legal? Don't blow my decoder buffer, right? I got a string, so I'm a receiver. I receive from the channel. Do we really know it's because it's a bit string or because of channel? You got to know one way or another, right? For standard, it's crucial you know your string is legal. For compression, they're not talking about channel, right? So it has to be legal. That's why this thing come out. It's the buffer model. You need a buffer model. So the well-known buffer model start with broadcast video. Basically, there's no jitter. Think about it, there's a delay, but no jitter. There's a fixed delay, right? No jitter. All right, so the model is still very simple. I try to repeat this, make sure you can memorize that. So this is the buffer, encoder buffer, decoder buffer, end-to-end delay is a C picture, right, in this relation. And the fixed frame rate in both sides, and also total delay is a C picture, okay? This is mathematical notion, very simple. Now, I want to impose constraints. So what are constraints? Then in the encoder side, I assume J's picture, every single picture, J's picture at the encoding time compressed data of this picture instantly drop into buffer. Okay, doesn't take time. Let's make it as an assumption in order to make the buffer really work. And decoding side, I do the same thing, instant removal. I try to depart the decoding process with this process. Assume the infinity, yeah. What do we really introduce the delta function as infinity, go to infinity, right? But you apply to the previous function, you will get this, okay? You see but look the green curve, look the previous one, green curve, now you change to what look like this impulse type of a curve. Actually, people, if you read the standard, you will see this in the standard. Very weird, because this impulse thing come in. It's come from here, actually mathematical model, right? So, all right. Now going to specific, actually in industry compression standard, what is the example actually use that, right? So one typical example really is that the impact to VDV model, right? Basically, bottom model is to really measure the timing of flow of the compressed data and decompressed pictures to fit in those models, timings, right? To make sure the string itself is legal. Right? Otherwise, you have tons of problems in the field you don't know how to correct, right? So. And basically, this model really saying that, okay, I give you a precoder buffer and also instant decoder. What I want you to do, I want you to specify the model, this 3-tube or this 3-tube. Either one will work. So this 3-tube, I say, hey, tell me your initial decoding time. Because fixed frame rate, once you know the initial, you know the next picture when you decode, right? And also the rate, what rate you want to specify for. And also total buffer size in decoder, only the 3 parameter. Actually, it happened pretty much in all the standard model, right? You go to AVC, you'll see it, HEVC, you'll see it. So, and also there's another model, you can do the equivalent. Let's say, how about I give you initial buffer fullness? I don't give you actually time, give you initial buffer fullness. That's also okay, okay? That's applied in the impact 4 part 2, all right? So in the model, so that's the model. Let's talk a little bit about the actual model, right? Applied. This is a typical one, basically VDV model. Let's go slightly deeper. I mean, I think people probably understand what the leaky bucket is. So leaky bucket model, in here, the leaky bucket is like this, right? This is the encoder side. We call it encoder VDV. VDV means that the video buffer Wi-Fi is the terminology commonly used for the impact to a video buffer, all right? So for this model, what do you do is that output, you always have fixed POR rate, as long as the buffer is, the bucket is not empty. Okay, when empty is 0, right? Nothing come out. So in this case, you will have this using maximum rate specified in the standard for this class of application as the condition. You pull out those bits. Okay, and other side, obviously, you have the instant dump in, right? Coded picture go in, right? The size never can exist in encoder buffer size, obviously. Okay, and then you mirror it. Mirror means that this encoder buffer is a leaky bucket, but decoder size is different. You pull out, for example, encoder side buffer on the flow, guess what? Decoder buffer usually will overflow, right? If you have same size, because it's a mirror, right? So you will get a mirror relationship in here, like this. Actually, you can calculate that. I don't need to go into the detail. What you get is like a plot like this. It's the time, then the buffer fullness. This is the model, not a real video will happen this way. It's a model. Validate the strings are legal or not legal. Okay? All right. So basically you initial 0, you pull in when you reach maximum, you begin to pull out the first picture. Then you go do it again with maximum rate. Once you hit the ceiling, you stop transmission, right? And go to the next time interval because you know where it is and pull out again. So this is create the model. So if you go back to previous formula, basically what you derive, you generate this. In the top one, this figure, you were found in the impact to spec, basically where it comes from, right? Basically, this is the way you build out those models, okay? And very fundamental, by the way, and unfortunately, actually, I have an email I can read. When for the people developing AV1, the people developing even don't know how this works, even writing out the emails, so I really want to show this thing really works for the new standard, okay? It's more complicated. I will show you why later. So in here, the key parameter really bit rate, buffer, frame rate, much simpler. Right? You can see linked to the 3-tube I mentioned about initial decoding time, rate, and the buffer size, right? It's related to that. So, by the way, I want to mention that actually, if you use this model, actually this model also fit in the theorem 1 we talked about earlier, the mathematical integration framework. This one will fit in that. Okay, it's a part of it. So, fundamentally, actually, for doing the encoder design, actually you're not using this model. You're using that integration formula in some form. Okay, obviously it has to be, in the discrete domain, right? Not in the continuous. That's for mathematical description. All right. So next thing I want to mention is that I want to do a simple comparison. So I think we have time to talk about this part. So I want to compare MPEG-2 VDV, right, buffer model with H.264, very popular standard. In there, they call coded picture buffer, CPB. Standard people always want to change a different term because the developers are different. They want to label different names. They're basically the same in theory. Okay, so MPEG classify the standard in profile and level. Very simple. The profile means different coding tools, right, grouped together called profile. And level really deal with different actual application, right? For example, in here we talk about standard definition video, right, compression. So you have a resolution of the band profile level really for SD video compression. Okay, so resolution here is 720 by 576 and 8 bits, and also YCBR 420, right? You probably know the bit rate in here specified in MPEG. The marketing rate is 50 megabit per second. Okay, then you have this weird 1.835 megabits as a VDV buffer. Okay, very weird number. So what the heck word you come out this type of number, right? Actually, it's a clever design. It's a history I like to share with you, and 25 frames per second. Here's the history. So actually, very few people in the standard still understand this. Actually, I would say that for the student, graduate, eventually will join industry, this is the thing you will need to solve. Actually, it's real problem. Genius. I would say it's a neat trick. So MPEG-2 is come out early 90. Okay, early 90, the memory is very expensive. Just like today, actually. Today's memory getting really expensive, this moment. And how expensive? We need to fit in standard definition, video decoding, decompression within 2 megabyte RAM. That's tiny. Okay, put it in perspective. Today, Android TV require 2 gigabyte. Okay, 2 gig, 1,000 times more required. Okay, that's good old days. That need only 2 megabytes. How to fit in? Okay, I'm decoding a picture, so the 2 megabyte is this many bits, right? 16 plus million bits. Okay. Then I need to define the buffer really fit in that. How will I do that? Okay, you got a 16 million bits minus I need a 3 picture to do prediction, front, back, middle, right? 3 picture. What is the picture size? 3x of the resolution. 1.5 color space, right? 420, right? Color space, and 8 bits per pixel. You subtract that. Then also, all the compression need quantization. Quantization is time using 8 by 8 block for DCT. So 8 by 8, you have inter, intra, different color components. End up you have 4 those matrix. Okay, each one is 8 bits. You subtract that. Then you have some implementation dependent bits for the header and those overhead, right? That counts for 10K bits. You subtract those together, exactly this number. Cleverly, by using the buffer model, they can fit entire SD decoding in 2 megabytes. Okay, the time. Really solve the problem. Otherwise, you cannot deploy product memory, it's too expensive. Guess what? In 2 years later, for AVC, okay, similar, over there, obviously, this relabeled profile level, they call level 3.0, still resolution, bit per pixel, color space, still identical, okay? Now they change. The bit rate is lower, understandable, right? New compression standard give you a lower rate. Your maximum rate definitely should be lower. However, they're throwing a lot of a buffer size. Now it's 10 megabits. Look, that's a good round number, right? Not like this weird number, right? The reason is that around year 2000, memory is really cheap. Okay, it's industry, so that's they will do because give me more memories I can map around and do whatever I like. However, it causes problems. Okay, now you get this buffer size of it's bigger buffer size. My rate is lower. Okay, what's the implication? That implies H.264 AVC allow more coded picture in the CPB, the coded buffer, which means larger C. Larger C, right? The decoding time, display time. What does that give you? More delay. That's exactly happened. Actually, around year 2000, right, the first World Cup in that time period, they tried to do simulcast of the standard definition and the HD coding, AVC standard definition code as the MPEG-2. Guess what? When the SD side shot in goal, the HD guys, they haven't seen it, right? It didn't show up yet. So that was in the trial. In the real broadcasting, they have to intentionally delay your SD transmission, to match up these two. So it does cause problems. So model, those type of model really can tell you what actually underlying problem is. Actually, in the MPEG-4 AVC, right, H.264, it does have model try to solve that, but not fundamentally, right? Basically, in there, they introduce, they call multiple CPBs, which means for the given single string, you can have a multiple compliant buffer model, which means if my buffer size is smaller, I can have less delay, okay? But in here, actually, in theory, you can see you basically specify a bunch of those 3 tubes, right? You can have n of them, right? And each one will satisfy those relationships. Each one will comply with the theorem 1, as we talked about earlier, right? But fundamentally, it doesn't solve the problem for design because in order to comply with the so-called profile level, we have to basically allocate the maximum buffer to fit in every application, right? Doesn't help me. I'm building a device, still same spending, right? So it doesn't matter. So actually, this gives you, this is really a secondary role, I will call. And also, by the way, I want to briefly mention the H.264 also give you decoded picture buffer, basically reshuffle the coded picture, right? I will argue this too, right, multiple CPB and also decoder buffer side, this is really a secondary role. You try to emulate actual application environment. It's not a primary role for the buffer underlying theory, right? It's just something people want to propose and put in there. So, but the more interesting, this one didn't show. More interestingly is this one. In the middle, you can see there's still instant decoding. Still have instantly decoding this assumption, okay? Here's a research problem actually I think is really valuable these days, okay? From the new standard, from AV1, people will begin to try to find a way to remove this. But mathematically, what is the best way to remove this? There's no models, okay? I tell you, it doesn't exist model. Industry already have something proposed to standard that's more or less I will call ad hoc. In the industry, we're in the industry, we do a lot of ad hoc. So that's basically, so why is that? Because this generation now, you have a real application really driving those. So many new applications like a two-way communication, right? Now more and more with video chat and two-way, those types of things, you need a very fast decoder to reduce the latency, right? You really have the demand, so you really need to bound the video decoding, not in 1 frame time, it's much shorter than that. Then you need a model. Otherwise, people build a decoder how fast you want, right? I have to hit the go, otherwise this thing can be, dead trapped, right? So you could, make your decoder really expensive, you sell nobody, right? Nobody will buy it, so sell to nobody. So that's basically one good research problem. So another extension I don't want to mention about the new standard also changed. The previous model I mentioned worked really well for MPEG-2 AVC, maybe some degree in HEVC, but for new standard, it doesn't work that well anymore. Why? Because in the old standard, basically you have this one-to-one correlation between decoded picture and presented picture. But new standard is not like this. For example, in the HEVC VP9, that's the implicit, they can allow the so-called hidden frame. Okay, AV1 is explicit, they allow that. What that means, look, this chart tells the best. All the green part is so-called hidden picture, which means you need to decode it, but you don't need to display it. Now you have a problem, which means for my timing notion, actually when I label it, which one I label on, okay? Your presentation only present displayed frame, okay? So what you need to do in here, I'll try to make sure really that you need to mapping those coded frame into a single entity, do those mapping. Then the theorem still will apply, okay? But become weird, okay? And some of the frame may not have a bit at all, could be 0, okay? But implied by other frame, okay? That's really, the model still applies, so the underlying fundamental thing. So there's another research problem actually in this domain because the new standard is going to this direction and it causes a whole lot of problem.
Just a quick question. When you say hidden, what does that when you don't display.
So basically what it does really is that people realize actually, a later part I will share with some data you will see. People realize that the coding itself doesn't give you much gain for video. Most of the gain comes from prediction. For certain frame, if I can prepare ahead of time, I can use in the multiple frame, right? For the prediction purpose, I can reduce overall, right, bits. So that's basically what I say. Basically in here, for example, for those 2 frames, I will pull out from this green part. I'm not doing anything else, okay? That's basically called golden frame, long-term frame, whatever frame they call. So in general, it's a hidden frame. You decode it, but you don't present for those frames, only for prediction purpose, okay? Try to help prediction. That's basically what happened in the very fancy, by the way. So doing compression, no fun. So next thing we'll talk about actually go through the IP network. Really is an extension of the system for the actually application. You can see from content provider, you know who they are, and going to different systems, satellite cable, and also these OTT guys, right? Sent to the server, then through the internet to the actually end user. What we're looking for in here really is that is a video transmission buffer and timing information, also the transmission rate. We talk about buffer timing, never talk about rate. I will give you one example. So make a very simple model really is that you have an encoder buffer and go through this complicated network buffer, then also all the way going into the decoder, right? We want to look into what is required buffer condition and also what preferred video rate, right? And also we can do the end-to-end delay estimation because time, because I have a limited time, I will not talk about the last bullets, right? Basically, very fancy. Last one is tough one to deal with. Okay, we have similar theory. Actually, now we look in between, right? Used to be encoder, then decoder, back to back. Now I have like a network buffer model being introduced here. And also I have a jitter and the delay being introduced here. I can tell you that actually you have similar theory, I call theorem 2, basically a little bit more complicated mathematical relation. You also can derive this buffer model for every picture not underflow or not overflow. Okay, very similar. Look at similar, right? But underlying thing is quite different. In here, in this theorem 2, you will have implicit digital being built in your decoder buffer. Okay, it's a common practice in industry. This underlying mathematics, right? How those things will actually work, right? You guarantee it will work once you comply with those relations. And very similar, you can see now you have a different set of parameters for the bit rate, buffer, delay, right? The jitter and frame rate, those are the parameters characterize this type of a system flow, okay? Go a little bit further, you see you can have a theorem 3. Now the difference is that I build the digital buffer explicitly. Okay, you also can have similar buffer condition as we described earlier. Okay, and here also similar set of the parameters, right? You have to deal with to describe the overall system. Bits flow through the entire system to ensure the video will work. Okay, one research problem in this area is very interesting. What I show in here is a single string with a bunch of pictures. Okay, but the internet never been that simple. Okay, you will have a lot of video being transmitted. Okay, if you build a complicated IP network, right? How you use those underlying theorem, right? Really develop a schedule mechanism to fit in multiple videos, multiple strings to optimize network transmission, right? That's really something very useful if there's a model exists, right? In that sense. So, yeah, it's a good. I think it's a good PhD topic. Anyway, so next thing we'll talk about, briefly talk about the rate. Now we look in the middle about the rate. So in order to do the rate in here, just one example, right? We can build up a very simple model. In here really is the a token bucket, right? Probably you're familiar with, and you can put m of them cascade together. This can be equivalent to a single one, right? So if you read the theorem, that's basically the case. In here, basically, we try to bound what the rate is, and also what if there's a bucket buffer, a size, what does those size will mean, right, for the real system, right? So for liquid bucket model, actually, it's a linear bounded arrival process, right? A little bit, using the model, and basically got bounded by this relation, very simple relation. Actually, now the rho for the rate, this rate, represent long-term average rate of the source, video source, okay? Then the B in here will be the maximum burst of the source, and we'll tell you that. And for this system, we want to also deal with the parameter. Okay, the key for the underlying theory really is that where's the minimum parameter, what those parameters are for the specific system. Now look in here, what do we want to determine? Really, this is row versus rate, and also actually a bunch of buffer and the delay and jitter, right? So that's basically the case. And I will skip this one. Basically, this one is saying actually, unfortunately, people generate a new standard. They are not they reduce the rate, but actually not doing better for the network because they can be more bursty. Okay, because of time, I'm not going to that. So people always think a new standard will do better, and not necessarily the case when you're managing a network. Okay, so if the new bit string is more bursty, it doesn't help me. You got an average rate is very low, how it's scheduled, right? And then you have to add a lot of delay. So anyway, so for bit rate, here's one example I call theorem 4. That's only one example to deal with rates. You can see here's the rate we're talking about. This rate only tied on the coded picture. There's nothing to do with the buffer at all. Okay, pre-coded picture size. You can see I only need 3 of them. Okay, I scan through the entire movie. If I can find the maximum of those C average, right, then I can determine this rate. This is far better using the actually average rate of the entire movie, for example, right? That's take a long time. You have to wait a long time in order to make sure your decoders are no glitch, right? This is contained solely on the video parameter, independent of network jitter and delay. So then one more extension going into ABR. This is commonly used in Netflix and also the YouTube, right? Those applications from the source, media encoder will encode multiple frames, you index it, and send through the HTTP sent to the client, right? You can build a similar model. Look, now it's more complicated in encoder side, which means I can have multiple resolution video being coded. When I transmit, I will switch in between, okay? But the underlying buffer model, they are almost the same, okay? And you can define those models to fit in the transmission so that you can have a different resolution bit rate and cascade together, transmit to you. Actually, that's exactly what we get today from Netflix and YouTube. Okay, that's basically what happened. So in summary, what we talk about in here really is about some of the key digital video transmission and compression parameters, basically, to fit in different type of systems, right? That's a fundamental for video transmission. From the resolution, bit rate per pixel, color space, and frame rate, bit rate, distortion, decoding time, presentation time, delay, and jitter, right? And also, the next thing with those parameters go in really is what the buffer condition, okay? What the decoding the buffer dynamics, right? Video buffer model, buffer rate condition for deliver IP video, right? What the rate condition, you can divide the rates. And you obviously can go more details to deal with the delay, and you can calculate ahead of time, right? This is very important to understand the model in order to set up the quality of service, right? In the next phase, as I mentioned, that OTT is today, eventually operator will turn on quality of service, you will get a better video. When that happens, you will need those parameters in order to guarantee you can fit in, best video. You can, right? With that, there's a bunch of reference. This is truly represents industry, a lot of industry IPs, patents, right? And that's it. I think I'll fit in time pretty well. All right. Any questions?
Any questions?
I try to make it simple, so go ahead.
One question, great talk. One question about the H.266 you mentioned. You're saying that's for VR, AR applications. So do you think there are any new dimensions we can study on top of what you already have for AVR?
They are. So I think for academic, maybe I'll use this. Yeah, that's nice. So, yeah. They are. So for academic world, I really believe that a certain underlying model probably fit in better for academic. I try to be frank, right? Basically, when you talk about MPEG standard body, try to specify this type of thing. And as a student, right, or as a professor in university, you can find the problem, try to solve it. But you directly involve those things will be difficult because they have 500 experts, right, from industry. They know all those things. And the trouble for academic is not because of knowledge at all. It's because our damn system is so complicated. In order to understand existing HEVC, AVC, and those, it will take a lot of effort. Okay, rather to do that, maybe address few issues the industry is not addressing. So one thing I mentioned, for example, for lower rate, relatively lower rate, I draw the RD curve compared with HEVC, right? HEVC. You bet, the next standard will happen the same way. Okay, they don't deal with the harder part when you go lower rate. Theoretically, what underlying technology can solve that? Why is that? Because they set up their own test conditions. It's only in the high side they can achieve. When you go lower, probably it's hard. There's not much of theory analysis, being done, right? So in that domain, actually, you can influence future application and the future standards, right? Really get a sense of those. So that's one area, obviously, it's quite useful. Another one really is that actually I didn't mention in here really is that how to link machine learning to evaluate compressed video quality, okay, with given framework. Given framework means that, okay, you got a HEVC transform, right, and the quantization, a bunch of prediction in huge size, right, 64 by 64, now go to 128 by 128, many computations, small block, large block, all those. So, and with that framework, right, can you classify good video quality with that framework, because that will help really test all the sequence. You can classify, hey, people come out of certain proposal, or come out certain encoder. Is this belong to good quality class or bad quality class? That are not being solved. Today it's very, I would say, dumb that the standard is doing. They train like 20 people and sit in a room, right? One after another, just virtually watch it. Then who believe that? You can buy out those 20 people, then you declare your standard is the best, so whatever. So that is actually hand to hand with actually what would be the better coding algorithm in those framework, because that's where directly related. Today it's very hard. For example, in the lunchtime we talked to some professors actually doing the students doing actually the mode decision, right, for encoder. Is absolutely right problem to tackle. Then say, hey, how you found the best mode? What that's supposed to mean? What is your performance measure? Right? You're missing other side. Actually, that is one thing not being solved in the industry or directly related to standard, but likely, industry will not be able to solve that because it's not their specialty, right, in that domain. So, and that's one example. Obviously, you talk about VR, AR. That's another example. We still have a big issue. For example, today, as you know, the VR to solve AR, VR, the first thing you need to solve really is like a 360 video, right? Regardless, it's fishbowl type of camera or using the camera outside, right? Shoot the middle, right? It's basically for the sport event, basically you have a bunch of camera outside to shoot the playground. So, how to code those, right? Today, you see the company proposing cube, easy ones, equal rectangular, right? Just like the globe, right? That's an easy one. Then Facebook has the cube format, and some other format come out. So what is the actually best one for the coding, right? Nobody tackled that. Very limited people really tackle that, right? So that's one area. So obviously, what I try to suggest really is that don't muck around with those coding tools, because a lot of energy. I don't think if it's for student, you are graduate there, because just not that practical, because you got 50 people to evaluate that, and a lot of work, and then you got a lot of opinions, so it doesn't fit in that space. Probably industry can afford that. So many areas. Also the new content. You mentioned about the VR, AR is definitely one area, and also. Can you combine, one thing is transmission, also another thing is that really, if you deal with 360 video, just think about that, because VR is more abstract, right? You go to any direction, you always have this inverse geometry mapping issue, right? Because it's not a flat frame anymore, right? So you have an angle, go up and down, left and right, they're different, right? So you have to do the geometry inverse transform, right, to map back to the viewpoint. So how to link that to compression. Look, standard convention not solving those, okay? And the people doing VR, they say, okay, give me the data, I'll render it. So as far as we go, right? So it's a lot of good questions, and in those new content format, right? We know there's this huge application, demand behind it, that's for sure. So go ahead.
Comment or a question follow up on the AR.
Mm-hmm.
If one focuses on building new encoders, right, which abides with the existing decoder, that should still be reasonable, right? I think, and there is no clear standard as to how one has to encode. As long as it's decodable, it's good and golden.
Yeah.
Is that accurate to say?
That's correct. That's correct. In general, that's the case. Actually, you're right. The situation is that you can fit in make sure your encoded content can fit in the actual decoder, right? But actually, in the industry, industry is not a dumb. I've just built this decoder and doing the only thing, right? So I can tell you in all the 4K domain, right? All the 4K decoder is capable to do 360 video today in HD, okay? You can do all those inverse, industry is definitely think ahead on those, right? But the reason for that really is that try to leverage as a product. When you build a product, right, you got a 4K capability. Can I do more? Always a boundary you need to push as a product, right? So that is definitely in there. So I think the better way to look this really is that you have to develop some method in encoder side to see, hey, if a very little hassle as an extension of future decoder product can support that, that should be the goal. Not say fitting existing, everything's existing. Then you will never advance, right? And your solution will be transitional if you do that way, right? Yeah, that's basically More question? Go ahead.
So you mentioned a threshold on the distortion value, like above which, if you have more distortion, then the video quality would be very low. For the context of VR, like where the user is viewing at a specific part, so the other part of the video can go beyond that distortion threshold.
You mean beyond that? No.
I think the question is asking us when you're viewing a specific part of a video, then you could probably be subjecting the remaining part of the video to a much higher distortion.
Yeah, that's correct. That's correct. So, that's actually a very good question. So actually, in the new standard we built up, all has a region of interest, right? For high interest region, you put more bits, right? Basically, bit loading differently, right? So that's already existing in the current standard, right? But actually, there are something you can do. Today, I don't think any real world encoder really doing, I would say, good segmentation and allocate bits, right, intelligently, right, using machine learning, those types of things probably doesn't exist today, right? That's obviously one area people can work on, right?
But I think your question specifically relating to VR is the fact that...
Well, VR, that's right.
Because you exactly know where you're watching.
That's correct.
What you're doing. That's the region that you can focus on.
That's correct. That's correct. Yeah, for two-way, yes. So probably if it's two-way thing, right? Two-way means that my transmission link, when I watch that part, because of my reaction time very quick, I can pull content. Answer yes. Basically, for different region, probably you can use the same trick as I mentioned. The encoder side really cleverly decide what actually bits will be sent, right? But in many other applications, may not be the case. The reason is that when you have VR, what they do is today really, I send the entire frame to you. Which part you render, it's the artifact, right? You do it later because I don't. Otherwise, because could be a delay issue, could be some other issue, right? You don't do that. Yeah, that's basically what happened, right? If you, two also come up. So if you that happened for example, on the YouTube, right? If you grab the YouTube 360 video, look at it as the entire frame, not just a portion, right? That's more to the transmission and application.
One more question.
Yeah, go ahead.
Comment on parallel encoding and decoding, like of a single video, like based on tiling or like different kind of.
Yeah, good question. So actually, it's a really good one. So. Yes, when the resolution getting bigger and bigger, so probably encoder is easy. Obviously, you can choose parallel processing, right, to do that. On decoder side, it's more tricky, right? So the problem really is that when you have those tiling multiple window, right, doing the tiling, what it means that your picture is pretty large For small one, you don't need, right? All the decoder can do it. When the picture is very large, you have to make sure all the boundary has to be really smooth because that's high quality video, right? If you don't do it right, you will see the boundary has those artifacts, right? That's tricky, okay? That's very tricky, and yeah, that's something you have to think about. It in the real world, that will kill you. So if you don't do it right, then say, what the heck? Why I need that, right? So.
Thank you. Why don't we actually take any other questions? We can do it outside. I think there's some refreshments that you can have, and Sherman will kindly agreed to spend another 15-20 minutes here, so you can ask questions. Thank you once more, Sherman, for a very informative.
Thank you very much.